Now we need to look at a few more examples just to make sure we fully understand how these situations work. Let's look at this example, 5 to the 4th times 5. Let's look expanded form, 5 to the 4th, 5 times 5 times 5 times 5. And now we have another 5 multiplied in there, and it looks like we have 5 to the 5th power. Now, if we know the answer is 5 to the 5th power, how does our addition rule work to get us to that kind of an answer? Well, we've got an exponent of 4 there, no exponent here. You might remember having seen this sometime in the past, that an exponent of 1 equals that same number. And now we see our rule work again, where if it's the same base, we can just add those exponents, 4 plus 1, 5. Okay? So when we see a number or a variable without an exponent, we know that it actually is a 1 there, always. And that sounds like something we can state using some variables. It sounds like another rule. A to the power of 1 equals. What would we want to write here to say, well, you can take anything to the power of 1 and it just equals whatever number that is that you started with. You could say a to the power of 1 equals a. We will see some situations in the future where we find some number, it just looks like a base with no exponent, and we will put a 1 there to show how all of our rules still work together perfectly. How about you try this example? Simplify, or you could say multiply, but let's basically apply what we know to these different things multiplied together and come up with some nice, small, simple looking answer. Okay, so pause the video and try this, and when you have an answer, let's restart and look at the answer together. I need to observe that this is only multiplication, and also I've got all the same bases. These are all x to some power. What do I know about this x here? Well, I could say it has exponent of 1, and now our rule, it's often called the product rule. You know I have a problem calling these rules, but I just can't avoid it at times. Product rule, that's what it's often called, to say if you have the same base, your answer is going to have also that same base, just add up all the exponents. So x to the 5th times 1 more would be x to the 6th, and then we have 2 more to make the 7th and the 8th, and our final answer, x to the 8th. Take another one here, and you can see that we have some mixed bases, x's and y's. Just try to apply the rule to the groups of the same kind of variable, if you get what I'm saying. Here's what I've come up with for an answer. Again, we have some variables with no exponents. I'll just throw in some 1s there, and if it's helpful, I do that. Anytime I see a variable with no exponent, I can put a 1. Now let's apply this product rule, where if I find all the ones that have the same base, so x to the 3rd with an x squared, now I have 3 plus 2, a total of 5, and it's this one over here that makes the 6th. So careful there that we're not starting to multiply those exponents. And again, I'm with you that it's beginning to feel a little bit odd here. This is a multiplication problem. But what do we do to answer it? We just add the exponents. And it's a little bit of a hurdle that we have to overcome to just make sure that we're doing things accurately. And it's helpful for me that I always think back to that expanded form. There's 3 x's and then 2 more x's and 1 more x for that total 6 x's all multiplied together. Let's get to the y's. Hopefully we're seeing 1 y with 2 more y's for a total of 3. And different bases, so we cannot go further than this. We definitely don't want to have anything to the power of 9. The different bases have to just stay separate, and x to the 6th, y to the 3rd would be our answer for this example. I'd like to take this opportunity to look at a few more of these examples that don't fit the rule that we've just been talking about to see how we'll handle those. But before we even get to those, just a quick little piece of information. Now, I would call this x to the power of 2 times y to the power of 3, or x squared with an exponent of 2. That's the one that is often called squared, and exponent of 3 is often called cubed. So this might also be read as x squared times y cubed. And I know I'll just go back and forth between those without really being aware of that. But just so that we're all clear on that, exponent of 2 we can call squared, exponent of 3 we can call cubed, power of 4 and 5, there are kind of names for those, but they're very rarely used, especially just when we're talking about this stuff. So those I would call power of 4, power of 5, or fourth power, fifth power, and so on. Okay, now we have talked about this situation a bit recently. We know that there's no way to combine those exponents when the variables are different. We would just place them side by side, lose that multiplication because it's always implied when we have variables side by side that they are multiplied together. Here's an example where we have numbers, but we have different bases. So again, we will not be able to combine those exponents, but what should we do in this case? Well, it kind of varies. Some folks would say, well, it's fine just the way it is, 3 squared times 4 cubed, but you might want to, and again, I think this will just depend on your instructor, whoever you're working for. I'm usually okay with numbers, just multiply them all out. And so I would suggest, well, 3 to the second power is 9, 4 to the third power is 64. Those multiplied together, 576. That's what I would do with this multiplication problem. But just to leave it as is, I think is 100% fine as well, unless it was come up with an actual number. Evaluate this. If it was evaluate, I'd have to say go for 576. How about this example? 2 to the third plus 2 to the fifth. We know that we cannot try to combine these exponents when it's addition. It's multiplication only. So what would we do in this situation? Well, again, I would, when they are numbers, evaluate. 2 to the third is 8. 2 to the fifth is 32, and then I'd go ahead and add those to equal 40. So just a quick recap of what I would recommend for these situations where we know we cannot use that product rule. What would I do? Well, if it's variables, we just jam them side by side. If they are numbers, then I just evaluate. Always use order of operations, so I do this exponent first, and then that exponent and multiply last. In this example, it would be do the exponents first and then add last. I hope you have a good grasp on what we've covered so far, but we've really only started to scratch the surface. So let's take things up one notch, and again, this will all be manageable. We're basing things on some things that we've already known and some very clear patterns that we can see. So let's look at this example, 3x squared times 5x cubed. We know that this 3x squared is telling us it's 3 times x squared. What do we know about this 5x cubed? That's 5 times x cubed. Now, do we have all multiplications in this list? We do. We have some parentheses in here, but we know as long as it's all multiplication, these parentheses can go. We can also begin to pick out some numbers and multiply them in whatever order we choose. We're going to pull out the 3 and the 5 out front. We'll multiply those numbers together, and then the x's will bring those together after the number. So the coefficient will come first, and then we'll have our variables after that. Can we do 3 times 5? Sure. 15. Just a quick one. Still, we're talking about everything all multiplied together. Multiplications here, multiplication there, and there. 3 times 5, 15. Let's use what we know about multiplying these exponential expressions that have the same base. 2x's times 3x's, we have a total of 5 of them. So this multiplication would give us 15x to the fifth. Not so bad. We will get to a point where we don't always write things in expanded form, but let's use the same rules. What is at work here? The rules that tell us that we can multiply these pieces in any order we want. So we will get to a place where we say, okay, I see the 3 and the 5. I'll multiply those coefficients. 3 times 5 is 15. And now I'll find x's. Every place that has a base of an x, there's 2 x's and 3 x's for a total of 5 x's. So it will be good to know why it works, and thinking about things in expanded form is a useful way to see how and why things work. But as we go through problems, we'll begin to do it this way, where we look at the coefficients, multiply those, and then one at a time we look at the variables and put those together. Okay, not so bad. This is doable. You're going to actually do it right now. So pause the video, give this one a try. Remember what we just talked about, that we can pull out those coefficients, multiply those together, and then one by one put those variables together into our answer. So pause the video and try, and then come back and we'll look at the answer together. Well, let's talk about what I see in this big, nasty problem. First of all, I need to look at the operations, that actually we do have all multiplication. I saw a minus or a negative here, but that's just telling us that our coefficient right here is a -2. We have all of these grouped in parentheses, so we know that there's multiplications there and there. So that is just a -2. We'll treat it as a number that we use when we multiply those coefficients together, but we definitely have a list of only multiplications. I will begin to do the multiplications in the order I like. Let's find these coefficients. 3 times -2 is -6, and -6 times 4, -24. The coefficients and number parts are done. Let's look for the x's. X squared, and here we have x. We know about that. It's x to the power of 1. So we've got 2 x's with one more, 3 x's. And now x to the third here, 3 with this 3, we have a total of 6x to the 6th. Next, y's. Let's just go in alphabetical order. We have 1 y there. No other y's. We do know that's a y to the power of 1, and we can put it there. It would definitely not be wrong if we had a 1 there, but usually we don't see it. Just like in this problem, the x that has a power of 1, we didn't see it there. We had to put it there or just know that it's there. We won't usually see it in our answer either, but when we see that y, we'll know that technically there is. If we wanted to see an exponent, it would be an exponent of 1. Let's just wrap this one up. Z to the third, z squared, that's a total of 5 z's. And that's it. Everything's taken care of. We multiplied the coefficients, and then we counted up how many x's and y's and z's, and there's our answer. Let me give you one more for you to try, okay? Just a quicker one. Take a minute, pause the video, try this one, and then we'll look at the answer. So we see 8 times -2 is -16. X to the third, and now here's x to the fourth, x to the 7th, and we have 1y, bringing down 1y. There's our answer. Now something just came to mind that I do want to go back to refer to. Up here, if you had a question about x, is this really x to the 1 or is it x to the 3? When it comes to exponents, they really only work on exactly what they're touching. That 3 is right on the corner of the z, so it applies only to the z. If I wanted this 3 to be referring to or to be used on the z and the x, I'd need to have those in a set of parentheses there with the 3 outside. And we'll talk about that at length very shortly. But just to be clear, if you had a thought back when we started this problem that that should be an x to the third, I'd say, no, that 3 is really only on the z. The x has that 1. Okay, now let's hop back here and talk about one last detail before we make our next leap. If we saw this kind of a problem where we did have an exponent outside, so exponent outside of parentheses is a way that we say it applies to this x to the third and also to that 8. But when we start to get into our flow of doing these problems, because they can eventually get pretty big and lengthy, I want you to know right now that when we see a problem that has an exponent outside of parentheses, there is something that we need to do first. That needs to be handled in its own way. If we saw this problem and began to do 8 times -2, it would be incorrect. So I have you on notice right now that when we begin to see problems where there is an exponent outside of parentheses, that needs to be handled in its own way. And in fact, we're going to look at that right now.